Okay, so let's start to introduce our first algorithm, which is called gradient descent. Okay, so our purpose for these two videos is to talk about the gradient descent method. So obviously it depends on the gradient of a function. So we all know that given a current solution, which is, let's call it x, okay? Suppose we have x as a current solution, then the gradient is simply a vector collecting all those partial derivatives. Okay, that's something we know. That means the gradient is an n-dimensional vector, right? And that means we are actually allowed to move along that particular direction. Okay, so consider this. We are talking about an n-dimensional optimization problem. Like for example, in this graph, we are talking about a two-dimensional optimization problem. Okay, the feasible region is a two-dimensional plane, and we move on that particular feasible region. So we are moving along some two-dimensional vectors. Okay, so at a specific point, for example here, okay, suppose I am here, I can actually ask myself whether I want to move along this direction or that direction or that direction or that direction. I need to make some decisions about which to move. Okay, in and I happen to see that, hey, my gradient is a two-dimensional vector. Okay, and in this particular example, okay, you see that this is my x, so this is my f of x, and we all know that gradient has something to do with tangent lines, right, with the slope, and it turns out that this is the tangent line of that particular point f of x. Okay, and the projection gives you the gradient in this way. Okay, oh, please remind yourself that your gradient is a n-dimensional vector. So your gradient is the blue one, not the red one. Okay, your gradient is a direction to move on your feasible region instead of something that is regarding your tangent or whatever. Okay, so we probably can propose one algorithm to you, is that suppose I want to search for an optimal solution. How about this? I randomly start at some point, and then I calculate its gradient. And then I ask myself, hey, probably I can move along the gradient. And I now want to ask myself whether moving along a gradient may help me find a better solution. Okay, so the proposal is I'm going to randomly start at a point, moving along the gradient at that point to see if I can improve. Okay, so now we need to ask ourselves, is a gradient an improving direction? Or maybe it's not. Then, of course, we don't want to move along that direction. So the proposition is here. Given a twice differentiable function f, its gradient is an increasing direction. Increasing direction. That is, if we move along the gradient, okay, I am currently at x, and I add the vector x by another vector, which is its gradient. And of course, when I add it, there can be a weight on it. So I'm going to change the value of a. If a is 0, I am still at the vector, the point x. If a becomes larger and larger, then I move along the gradient direction, forward and forward. Okay? Increasing direction is saying that if I move along the gradient, then as long as a is small enough, then I will get larger than the point f of x. Okay, so that means if I move along the gradient, I am guaranteed to increase the function value as long as I do not move too far. Okay, so what does that mean? Suppose I have a function like this. Okay, then at any point, I can calculate my gradient, which is this direction. Okay, so that means I want to move along this direction. Obviously, it's possible that after I move for too far away, I probably will get decreased. But this proposition is saying that as long as you move along the direction and do not go too far, then you are guaranteed to increase. So that's the proposition. Okay, very quickly, let's see why it is true. So we know that in your first year calculus textbook, we have this equality. So what's that? The limit between the difference of f of x plus ad minus f of x divided by a. If we let a goes to 0, then we get its gradient times this vector d. Okay, here a is a constant, but d is a vector and x is a vector. So x and d, they are vectors. Okay, that's why after we do this, it gets to the gradient. It gets to the gradient of f. And here we are doing an inner product. Oh, there should be a transpose of t. Okay, so because we have that, so that means if I actually plug in d by its gradient, okay, so I replace d by its gradient, then here I'm going to get a gradient times a gradient, okay, or the inner product of gradient. And of course it is positive as long as the gradient is non-zero, okay, as long as the gradient is non-zero. And also in this case we know if a is close to 0 enough, then the difference is going to be positive. Then it concludes that if we move along the gradient and do not move too far, then we are guaranteed to increase. Okay, so in fact it's very easy to show that the gradient is not only the increasing direction. Actually, among all those increasing directions, gradient is the fattest increasing direction. Okay, so given that the gradient is an increasing direction, that's good. Now we know we should not move along the gradient. Instead, we should move along its opposite because we are talking about the minimization problem, right? But still, this method is good because at any point, I try to improve it. And the idea is very simple. Find its gradient, which is well defined, and then move along the opposite direction. Okay, so now given a current solution x, in each iteration I'm going to update x to the next solution, which is x minus a times gradient of f of x. So this is my gradient. I want to move along its opposite direction. That's why this is negative. And the last thing remains is to choose a value a, which is called the step size. So in each step, I want to move for a certain length. That depends on my step size. If a is large, then the step is large. Otherwise, we just move a little bit. So we will keep doing that, keep doing updating until the gradient of a current solution is 0, or technically is very close to 0. Okay, then we reach a stationary point, and in many cases it's just our optimal solution. Okay, so we haven't told you how to choose an appropriate value of a, right? So before we do that, let's see some examples. So here, the first thing I want to give you is a bad example. So let's use this function, this quadratic function x1 squared plus x2 squared as an example. We all know that if we draw it, then we're going to get its isopropyl lines like this, like this, like this, right? These are the isopropyl curves, and an optimal solution is here. Okay, Now let's see what's going to happen if we apply our algorithm. Suppose we start at x0, which is 1, 1. For no reason, let's assume I start at this point, which is 1, 1. Now, my gradient in general can be found because the function is here. So the gradient is nothing but 2x1 and 2x2. And then if I plug in my x0, 1, 1, I'm going to get my gradient as 2, 2. So my gradient is this direction. Okay, this is gradient of x1. And this tells me that I should move along this direction, right? The opposite of the gradient. Now let's see if I set a, it's a, sorry, it's a. If I set a to be 1/2, what's going to happen? Then I'm going to move from x0 to x1, which is from the current solution minus 1/2 times my opposite gradient. Then I'm getting to 0, 0 directly, which is optimal. Okay? In that case, this a is wonderful. On the other hand, if we set a to be something else, then what's going to happen? For example, if we set a to be 1, then of course we're going to move a larger distance. And you can see that we're going to move, if alpha is 1/2 is here, if alpha is 1 is exactly the opposite with respect to the origin. So immediately you see we are having a too large step. Okay, so what does that mean? I'm going to move to here, and if you calculate their objective values, it's actually the same. So we tried to improve, but actually we didn't because we moved for a too large step. And what's worse is that if we keep iterating at this moment, if we calculate the gradient at x1, then actually we will see that the gradient at x1 is -2 and -2. So if we use the same a to do the iteration, we will move to 1, 1 again instead of, and we will pass through the optimal solution again. So that's why the algorithm will never converge, because we'll move here, 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 here. So this very tiny example simply tells you that choosing the step size can be very important, even though moving along the opposite direction of gradient is somewhat smart, but you still need a clever choice about your step size. So in the next video, let's talk about how to choose a step size. Thank you.